So, so I have a device under test, and I connect my measurement setup, which also displayed to this device, and I measure. And let's assume I measure the same experiment twice. Will I get exactly the same measurement in these two measurement sessions? Will I measure exactly the same? Okay, so there is a good consensus here that indeed, yeah, I won't measure the same thing. And why is that? Because I'm actually measuring noise. So in fact, the system I'm measuring, I'm not just measuring the power consumption of the secret, I'm also measuring other things and getting us all together in my device, in my measurement arm. So there are three general sources of noise. One of them is switching noise. So switching noise means some kind of other calculations or computations which are going on together with my secret computation. For example, there might be a secret. Every time I turn on the engine in my car, it might be calculating, all the signatures and public and DRM and versions of all the computers in the car. But on the other hand, it's also doing this this ignition cycle, which is very, very noisy. So every time I try to measure, I measure something else because it's so powerful. So there are two kinds of measurement noise, switching noise. There is what is called correlated switching noise, which happens every time I do my secret measurement exactly at the same time some other measurement happens. Could be, I'm typing on my phone, and the phone wants to make a click, 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 click sound. So the click, click calculation is always at the same time. And there's also uncorrelated noise. Uncorrelated noise means that it just happened that while I was doing my secret calculation, an email came in, and the computer decided to, play a sound. What is nice about the uncorrelated switching noise is that you repeat the measurement many times, it gets averaged away. But if it's correlated, you cannot average it away, which is kind of sad. Okay, another kind of noise is measurement noise. Measurement noise means that I'm actually using an imperfect system to measure. So I have a scope or a ruler or something. This is a physical artifact in the physical world. It has a connection to the device under test. I'm measuring all sorts of stuff on this cable, and there's some kind of digitizer or sampler or whatever. There's a very nice experiment when you take a degree in physics. One of the first labs in physics is each one of the students gets a metal ball and a caliper, and they're supposed to measure the diameter of the metal ball. And they measure it 3 times, of course, every time they get a different measure, which is very insightful, you see, because there's measurement noise. And the third thing is called thermal noise. Thermal noise is the craziest noise. And basically, thermal noise is caused by the fact that electrons are very strange and crazy particles. And electrons have the tendency to disappear and reappear somewhere close to where they were previously. This is how they roll. And the higher the temperature is, they do it to a higher distance. And then you have all sorts of things like electron flowing in one cable and then deciding that it wants to jump and flow on another wire. Or some kind of radiation from electrons moving around in the air. And thermal noise, as the warmer it is, the crazier the thermal noise happens. And this is one of the reasons that your CPU needs to cool itself down. So it can't get too hot, because if it gets too hot, even before it starts making the happy smoke, there start to be measurement errors. There's a very nice paper where researchers shown a lamp at a smart card, an incandescent lamp. And the heat from the lamp after a couple of hours was enough to cause very, very small errors because of thermal noise. So these are sources of noise. And what happens is when I measure, I don't just get the static and the dynamic, I also get the noise. And the noise is a function of the time, but it's not a function of the calculation of the secret. So I really hate this noise. So can anybody suggest some kind of technique of dealing with the noise. I have the noise. I don't like the noise. What can I do? What can I do to reduce the noise? Okay, so one suggestion is to take many measurements and do an average of them, and then I will be taking good care of the uncorrelated switching noise and the measurement noise and thermal noise, because if I assume that the noise is it has a mean, maybe zero, maybe not zero, but every time I do average, the variance is going down, and I will be able to get the signal better. Okay. Any other things I can do other than that, because that won't help me against correlated switching noise? What else can I do? Any other crazy ideas to reduce the noise? Okay, so Shimon is saying something very, very good. I can take my setup and put it somewhere where there is less thermal noise. So if I take my device and freeze it, then I will get less thermal noise, less measurement noise. That's a good idea. I can also prevent some kind of radiation noise if I put the device inside what is called a Faraday cage, which is kind of a container which absorbs all sorts of electromagnetic radiation, and then I will also be able to focus on my device and not on other things which are going on. Okay, let's be now more invasive. Any other invasive ways of? Okay, if I want to be really, really crazy, how can I reduce the noise? So one thing I can do, and I can suggest if you want to be invasive, is to modify the device and kind of damage it in a way which either increases the signal or reduces the noise. For example, if there is kind of a filtering layer, I can strip it away. If there is a noise generator, I can shut it down. If there is a function that leaks some kind of side channel data, I can cause it to run 1,000,000 times. This is called SGX step, which is crazy. I can make it run 1,000,000 times instead of once. So I can break my implementation so the secret stands out and the noise is reduced. And one of the things that I can also do is instead of measuring, I can tap the lines directly, but who says that the secret is in the lines I can tap? Okay, maybe there's a noise generator and a CPU, and the secret is deep, deep inside the CPU, right? So it depends on the attacker model, of course. Once you do this, you start getting into trouble with your system document, indeed. But one thing you can do is move from power analysis to EM analysis. And EM analysis is a very, very close neighbor of power analysis. Basically, other than a very small tweak to the workflow, which I'll show you, you use the very similar techniques. And what is the idea? So there is a law that says that if you take a piece of conducting wire and you move current through this conducting wire by the left-hand law, which might be turned into the right-hand law on your screens, we will create a magnetic flux around the wire. There is a magnetic flux around the wire. So this magnetic flux, it doesn't have to be a variable current. Any kind of current causes a magnetic flux. This magnetic flux doesn't travel very far. It's very close, but it's a function of the current. So if I take a magnetic field probe and place it really, really close to the device I'm going to test, I can measure a function of the current, which is as good as measuring the current, which is as good as measuring the power. Now, the advantages of this are two. First of all, it's non-invasive, which means I can sell it a little more easily. And the second, it's very, very localized. It's very, very focused. So I can do what is called cartography. I can look on my device under test and find the exact point where I get the best leakage. And if there's a noise generator somewhere else, I will basically ignore it. So this is the magnetic field. The advantages, I just told you, the disadvantage is that it doesn't travel very far. So you have to be very, very close, almost touching, which sometimes isn't possible. The other thing which happens is that if you have a variable current, then you cause an electromagnetic wave. So the electromagnetic wave is caused by changing current, and the electromagnetic wave travels a lot farther than a magnetic field. And you can measure it using like radio antenna. And this is a little more impressive to your system architect, because in my master's degree, which is like in 2006, I did power analysis from a couple of meters away. I can only imagine what they can do today. So if you have the right directional antenna and amplifier, you can get EM measurements quite far away. Of course, the disadvantage is that your antenna will be picking up all sorts of other crazy things which are happening. So you need a lot of signal processing and a lot of measurements, but still it's non-invasive variation on power analysis.